In this video, we will try to understand the working of the common layers which are available in any convolutional neural network. So you will find four different layers. First one is a convolutional layer. So this is required for extracting the important features of an image. Then you have a pooling layer to optimize the dimension. Fully connected layer and softmax layer you will find in the classification part. And softmax layer, finally, it gives out the probability scores for each of the image classes. This slide shows the architecture of AlexNet convolutional neural network. AlexNet has a simpler architecture when compared to most of the other widely used CNN pre-trained models. For example, if you compare AlexNet architecture with Inception v3, this has got only few layers. If you count the number of convolutional layers, there are only five convolutional layers here. Then there is a pooling layer after most of the convolutional layers. And then in the classification part, you will find the fully connected layers, and finally you will have the softmax layers. So we'll try to understand the working of each of these layers in the next slide. This slide shows one convolutional layer. In the previous LXNet architecture, you have seen five convolutional layers. So let us try to understand what each convolutional layer does. So if this is the first convolutional layer, so input will be an image, and I'll be taking a small segment of an image just for explanation purpose. And the height of this is 6, width is 6, and there are 3 channels corresponding to red, green, and blue. So if you look at the convolutional layer, so this performs 3 different operations. First one is a convolutional operation whose notation is shown here. This is nothing but a convolutional operation. After that, the second operation is a constant value called as a bias is added to output of convolution. Then after that, a kind of a rectification is done. So 3 operations will be performed by one convolutional layer. That means each of the convolutional layer that you have seen in the LXNet architecture has to perform these 3 operations. Now, to understand what convolution operation, like how convolutional operation is performed. So in order to understand convolution operations, let us take this example. So I have an input image of 6 by 6 and the filter of 3 by 3. So convolution operation requires a filter with which the image pixels are multiplied element wise. So how this is done? So if you take this image has some pixel values. So we start from this position. Okay, so if the filter is aligned with these pixel values, then element wise multiplication we do. That means the pixel value will be multiplied with these coefficients or these filter weights. Okay, so you get 9 different products and they are summed up to get a single value. So for example, 1 into 1 plus 1 into 1 plus 2 into 1 plus 2 into 0. So this way we get 9 products, and by summing it up you get a single value. In this case it's -1. And after each computation we shift it by 1 pixel to the right so that it will be aligned with these image pixel value, and you get this output matrix element. And similarly we shift it by 1 pixel value. If we shift it by 1 pixel value to the right or left after each computation, we call it as a stride equal to 1. So stride indicates the shifting parameter. Now if you observe the dimension of input image and output matrix has a smaller dimension when compared to this. But if you want to have the same dimension as that of input image, you can pad zeros here at the border, so that so dimension of this matrix will increase. Instead of 6 by 6 it becomes 8 by 8, and we can start aligning with this particular pixel values, so you get a 6 by 6 output matrix. But in this example there is no zero padding done, and the stride is 1. When the stride is 1 and no zero padding, you get 4 by 4 output matrix. If the stride is 2, the dimension of output matrix will reduce, because after each computation you shift it by 2 pixels and again you compute a new output pixel value. So this particular image, if this is the image and if you pass it through this filter, you get horizontal edges. That means if I want to extract horizontal edges from this image, I can use these filter values 1, 1, 1, 0, 0, 0 and -1, -1, -1. And similarly, if I rotate it by 90 degrees, that means if the first column is all ones and the last column all -1 and the mid column is zeros, then I get vertical edges. That means by having different set of filter values or weights, I can get different features. I can extract different features from an image. Now we understood how convolution operation works. So let us see one convolutional layer. As I mentioned, one convolutional layer has to perform 3 different operations. The first operation is convolution itself, which already we have seen, followed by adding bias and rectification. Now, if you take the first convolutional layer, so there are 3 channels as I mentioned earlier, corresponding to RGB. So you need 3, this filter also should have 3 channels. So it's denoted as 3 by 3 into 3. The last 3 indicates the number of channels that you have. Now, if you look at the output, it's a 4 by 4, just 4 by 4. That means there are no 3 channels here. So what we do is we take this as a cube. So we perform convolution between this filter and this filter. For our image, we have a separate 3 by 3 filter, similarly for green, similarly for blue. And we get 9 into 3, that means 27 products, and we sum it up to get a single value here. So similarly, we shift it by right by 1 pixel and you get this value. So though you have 3 channels here, the output of this will have only 1 channel. And after that, once you get 4 by 4 matrix at the output of each convolution operation, you add a constant value to this, and that means for each of these a constant value which we determine during training process will be added, and you get a new output matrix of the same dimension. Then this matrix may have some negative values, so we rectify it to get a rectified output. So this is called as ReLU. ReLU is an activation function. There are other functions also exist. So this is widely used function called as rectified linear unit. So what it does is all the negative values are rounded up to zeros and the positive values are retained as it is. Now in this convolutional layer, there are 2 filters which are considered. So you have a filter 1, filter 2. Okay, but AlexNet first convolutional layer, if you take, there are 95 filters. So it has 95 filters. Similarly, Inception V3, the first convolutional layer, has 32 filters. That means each convolutional layer, it may have number of filters of different dimensions. Now what is important is how many parameters we need to train during the training process. If you talk about this convolution layer, this example, there are 20, each filter has 27 weights, that means 27 parameters plus 1 bias, that means 28 parameters for each filter or each channel, I can say. And similarly, you have 2 different filters. So 28 into 2, that means 56 parameters have to be trained during the training process using backpropagation algorithm. And in this example, the number of filters are 2 and the stride is 1, 1. If the stride is 2, 2 or stride is 2, then the dimension of output matrix will reduce and no zero padding is done. So therefore, output matrix will have a smaller dimension when compared to this. To summarize the convolutional layer, as you can see, it has to perform three different operations. First, it performs a convolution operation. It performs biasing, that means a constant value is added to each output of convolution. Then a rectification is done. Convolution operation is used for extracting the image features. For multiple features to be extracted, you can have multiple filters with different coefficient set. Then you need to add a bias so that your output can fit best for the given data. It is just like you add a constant value in the linear equation y equal to mx plus c. And similarly, the last operation will be a rectified linear unit which rounds off the negative values to 0 and retains positive values. The purpose of pooling layer is to reduce the dimension in x and y axis. In this example, a 4 by 4 input matrix is chosen, and so you are supposed to reduce the dimension in x and y direction. So pooling layer also will have a filters of maybe 2 by 2 or 3 by 3 size, but these filters will not have weights or parameters like a convolutional filter. So there are no weights to be trained in this case. So you can also have a stride 1 or a stride 2. Stride indicates the shifting operator. So if you take this example, in this case the input matrix is 4 by 4 and the filter size is 2 by 2 and the stride is 2. In this case, this is the initial position of the filter. As I mentioned, the filter does not have any weight, but it's just like a window. You will be able to see the 4 elements. And in the case of max pooling, there are two types of pooling operations. Either you will have max pooling or average pooling. The max pooling is widely used. So in the case of max pooling, the maximum value out of 4 will be chosen, and the output matrix will have this maximum value. As you can see, the input matrix dimension is 4 by 4, but at the output you will get 2 by 2 if the stride is 2 and filter size is 2. So the different colors are given so that it's easy to understand. So out of these blue pixel values, the maximum value will be 9, so this will be 9. And similarly here, the 2 will be the maximum value, so output matrix element will be 2. So similarly 6 and 3. So this is how it's going to be. So when you talk about average pooling, inception layer has max pooling as well as average pooling layers. So if average pooling layer is available, then how it works? It takes the average value of these 4 elements. For example, 1 plus 3 plus 9 plus 2. So altogether it's 15. So 15 by 4 will be 3.75. So average value will be replaced. So this is how a pooling layer works. Remember, pooling layer is meant for reducing the dimension in the x and y axis, because finally at the output of convolutional neural network you need a 1D vector which gives the probability scores of n image labels. Though you have 3D matrices in the beginning, but that has to be converted into a 1D array. The fully connected layers you will find in the classification part of convolutional neural network. And if you look at the dimension of fully connected layers, so it will have a one-dimensional vector input as well as one-dimensional output vector. Now, if you look at the output of feature extraction part, you may get a 3D array, and that has to be converted into one-dimensional vector by a flattening operation. So this particular vector, input vector, you can call it as a feature vector, because this vector will have all the features extracted by the feature extraction part or by convolutional layers. And if you want to compute the number of parameters this fully connected layer has, so it's very easy to compute. You just multiply the number of inputs with the number of outputs. In this case, 5 into 3. So that's 15. So there will be 15 weights, because as you can see here, all the input nodes and output nodes are they are interconnected, and each interconnection has a weight. So therefore the number of weights will be 5 into 3, 15. And each output will be then, so you will have a bias which will be added to each of these outputs. So this is the mathematical equation which is shown here. So yi represents the number of outputs of fully connected layer. So if we talk about each convolutional neural network, it will have multiple fully connected layers in the classification part. So fully connected layers will get the input from the feature extraction part. That means after convolutional layers and pooling layers, and that will be flattened into a one-dimensional vector, and that will be fed to fully connected layer. And output of fully connected layer, finally, it will be fed to uh, a softmax layer, which will compute the probability scores or the confidence scores for each of the image class. Softmax layer is the last layer in convolutional neural network. So purpose of this layer is to generate the probability scores for each of the image classes. If you take this example, so in this case, there are 3 image classes. That means you need to classify between 3 classes, cat versus dog versus tiger. In that case, the softmax layer should have 3 different outputs, the each output corresponding to each of the image class. For example, if the input image is cat, then the probability score for cat will be higher. Let us say if you assume that the first output will be the probability score for cat, and similarly the second one for dog, and the third one for tiger. In that case, if the input image or if the test image is cat, and if your convolutional neural network model is properly trained, if the weights are optimized, in that case the y1 will be high, because that's the probability score for cat. And similarly, if the input image is dog, then y2 will be higher than y1 and y3. So similarly for tiger. So if the weights are not optimized, that means if the model is not working properly, or sometimes your model may give a wrong output. In that case, if the input is, let us say, cat, you may get a lower probability score for y1 when compared to y2 and y3. So this is possible. So now when you look at the number of inputs and outputs of softmax layers, that's going to be equal. If you are classifying 3 images, 3 classes, in that case there will be 3 inputs and 3 outputs. Output will be probability scores, and the input will be the features which you get from the fully connected layers. The fully connected layer, the last fully connected layer output will be same as the number of image classes. As I mentioned, CNN may have more than one fully connected layer. The last fully connected layer output, number of outputs will be same as the number of image classes that you have. And this is the mathematical formula that you can use to compute the probability scores. As you can see here, so in order to compute the output, each of this output, so it requires all these 3 values: exponential e to the power of minus 21 plus e to the power 0.47 plus e to the power 1.72, all are summed up. Then you divide it from e to the power xi. So this is how you can get the probability scores.